So we're going to talk about the cosine equations today. And here's the good news. First of all, as soon as I get my camera lined up somehow. Okay. Well, anyway, the good news here is that, at least in my opinion, dealing with the equations involving cosines is a little bit easier than dealing with the ones involving sine. In fact, I kind of did sine first because I think it's more complicated. And you might think that's weird. Why would we do the more complicated thing first? Well, in this case, I kind of think thinking through sine, once you do that, you can think through all of these other cases much more easily. So just like with sine, we're going to start out with a simple question. What if I wanted to solve the equation cosine of t is equal to some number c? Now, I'm not going to give you a specific example this time. I want to just think about this equation in general, because we've already seen what happens with sine. Well, the general thing we would like to do is we want to write this using the cosine inverse of c. But just like with sine, we actually get a whole family of solutions. There's going to be infinitely many solutions to this thing. And let's think about why that is. There's two kind of ways to visualize what's going on here. One of them is to use the unit circle, which takes me a minute to draw because, as you know, I have no artistic skills. Okay. The cosine of an angle is the x-coordinate. So we're actually looking for angles t that have terminal points that I just marked here. Those terminal points should have an x-coordinate that is equal to c. Now, cosine inverse is in 0 to pi. And notice that if I get one solution in the top half of the circle, I get another solution in the bottom half of the circle. But what is this angle? Well, it's just minus t. In other words, if I have one solution, I get a second solution by just taking the negative of it. So what does that mean? This means we get our two base solutions are going to be that t is equal to cosine inverse c and negative cosine inverse c. Well, I can consolidate this whole thing into just plus or minus cosine inverse c. Compare this to what we had to do with the sine function. With sine, when we said sine t is equal to c, there we had to say, well, t could be equal to sine inverse c, but it could also be equal to pi minus sine inverse c. And this, well, we couldn't really consolidate these so well. The cosine is a little bit simpler because we just take cosine inverse and negative cosine inverse. That's the same as plus or minus cosine inverse. Hey, we're done. Okay, somewhat simpler, somewhat shorter. I mean, I think it's a little bit shorter. Just like with the sine function, though, we do get kind of three different cases that are going on. And you can see these cases by thinking about what happens over one cycle. So for -1 less than c less than +1, we get two solutions per cycle. If c is equal to plus or minus 1, then we get solutions of either 0 when c is equal to 1, and then we have to shift that by 2 pi k, or we get pi plus 2 pi k when c is equal to -1. So in this case, we kind of just get one solution per cycle. And finally, for the absolute value of c being bigger than 1, well, in that case, we get no solutions. So, okay, it's not really that much different than dealing with sine equations. Let's just take a look at these examples here. or these examples, well, the examples that I'm about to show you, just to kind of get used to what you do when you're dealing with the cosine problems. So if I wanted to solve cosine of t is equal to -3/4, my solutions here would be t equals plus or minus cosine inverse of -3/4 plus 2 pi k, because of course I have to shift all of my solutions by 2 pi k. Now, that's it. I mean, there's really nothing more to do with this particular problem, because the variable is the only thing inside of that cosine. Just like when we were dealing with the sine examples, though, you can have more complicated types of situations crop up. So let's see if you can handle this problem. What if I said that 5 cosine t is equal to 3? So let's see if you can solve that problem. Pause the video for a minute and take a look at this and see what you can do. Okay, so 5 cosine t equals 3. Well, this is going to have, first of all, I'm going to isolate the cosine on one side, so I don't know what I'm doing writing a 5 there. I'm going to get cosine t equals 3/5. So my first step, just like when we were working with equations that involved sine of t, is I want to get the trig function by itself on one side. And then this is going to be equal to 3/5 in this case. Well, now I'm back in the situation that I was in the previous example, and I can say that t is equal to plus or minus cosine inverse of 3/5. Those are my two basic solutions, and then I have to shift all of those by 2 pi k. Take a look at another example here of some subtler things that can happen. What if I had the cosine of t squared plus 2 equals, let's say, 1/3? Well, the thing that I want to remember here is the whole angle inside is t squared plus 2, and that's going to have to equal plus or minus cosine inverse of 1/3 plus 2 pi k. So it's like what we were doing in the previous examples. The difference here is that the angle inside of the trig function that we're looking for isn't just the variable anymore. It's actually this whole expression written in terms of the variable. And so we get t squared plus 2 equals this large kind of messy looking thing. But remember, even though it kind of looks like a mess, it's really just, it's the same thing as what we get whenever we deal with any of these kinds of problems. It's just those angles which would give me a cosine of 1/3. Now, in order to solve this, we're going to say that t squared is equal to plus or minus cosine inverse 1/3 plus 2 pi k minus 2. And that means that t needs to be equal to plus or minus the square root of plus or minus cosine inverse of 1/3 plus 2 pi k minus 2. Now, there's going to obviously be some restrictions here, but to be honest with you, I wouldn't bother writing them out explicitly. Personally, I would just say, remember, the thing inside the square root is going to have to be a positive number or 0. It cannot be negative. So we do need to have the condition that this thing has to come out to be positive. The problem there is that, how is this going to come out to be positive? Well, I think that as long as k is bigger than or equal to 1, we're fine. But we can also allow k equals... Actually, in this case, you may not be able to allow k equals 0 either. So I think this time it just comes out to be k has to be bigger than or equal to 1. But you don't really need to worry about it too much. Usually you can just say, look, this has to be defined. So it has to come out to be something where the stuff inside the radical is bigger than or equal to 0, and you don't have to worry too much about how do you write that down. Let's take a look at another example involving the cosine. What if I had something like 7 cosine squared x is equal to 3? Well, I'm going to give you a minute to see if you can figure this one out. So pause the video for a minute, try this out, and see what you get. Okay, so the first thing I would do is simplify this to be cosine squared x is equal to 3 over 7. This is going to become cosine x equals plus or minus 3 over 7. This is going to end up having solutions, plus or minus the square root of 3 over 7. I forgot my square root. That's kind of important for this problem. Now, this is going to end up having a whole big family of solutions here, because what we're going to get now is that x can be equal to plus or minus the cosine inverse of plus or minus square root of 3 over 7 plus 2 pi k. So we've actually got an enormous family of these things, because there's a couple of different options here for taking plus or minus options, but the solution actually has this very nice compact way that I can write it. This is literally the whole solution, even though there's so many different choices involved. So, if you were able to deal with the equations that involve the sine function, then you should be able to deal with these involving the cosine, as long as you remember the new rules that you have for dealing with the cosine. And for me, I find that the best way to remember those rules is to remember where they come from. I mean, honestly, if I just tried to memorize, okay, which one is it that has the complicated one and what is the rule, it becomes rather tricky for me. The way that I remember these rules for, is it plus or minus cosine inverse, why is it sine inverse, and then pi minus sine inverse, always come back to your unit circle. Okay, so if I have my unit circle, if I want the cosine to be equal to c, then I get plus or minus some angle, because this is t, this is the angle minus t. But if I want my sine function to be equal to some angle, well, now I'm talking about the y coordinate. And this is more complicated. I get one angle t, and then I get this angle here, which is going to be pi minus t. So that's how I remember the rules. Which one does the plus or minus? That's the cosine. Which one is the inverse and then pi minus the inverse? Well, that is the sine function. So if you remember your unit circle, then you can remember these rules without having to do too much work memorizing them. If you don't remember your unit circle, then you're just going to have to memorize everything directly, and it's going to be a little bit trickier. But you can do it. I just personally hate memorizing stuff. I would much rather try to kind of remember things by sort of remembering where they come from, because my memory is terrible. All right, now, what about in the situation where we have secants? If you remember what we did in the last video involving sine functions and cosecants, then the trick that I'm about to show you might be something that you've actually already thought of. You could kind of work this out on your own. So if you want to take a minute and think about how to work out this trick on your own, then I would really encourage you to do so. How could I turn an equation like secant of t equals c into something that involves cosines? Were you able to think of something? So the answer is, we remember that this is equivalent to saying that the cosine of t is equal to the reciprocal of c. And now all of my equations that involve secants, I can flip them into equations that involve cosines, because I just have to get it into secant equals something, and then I can turn it into cosine equals something, and That way, I never have to worry about writing it in terms of inverse secants if I don't want to. If I did want to write it in terms of inverse secants, I could say, okay, well, another way of thinking about this is to say that it's going to be t is equal to plus or minus secant inverse of c plus 2 pi k. So we get exactly the same kinds of things going on here as we did for the cosine. Similarly, when I showed you that trick for the cosecant, you could also use cosecant inverse. You would just have to do cosecant inverse and then pi minus cosecant inverse, just like you do when you're using sine inverse. But personally, I would say, if it makes it easier for you, just flip it all into sines and cosines. Don't even worry about dealing with secants directly or cosecants directly. So what about tangent and cotangent? Well, tangent and cotangent are a little trickier. Actually, they're not a little trickier. I don't know why I said that. A little different is what I should have said. The main difference here is if I want to think about an equation like, let's say, tangent of t is equal to c, this is always going to have one solution per cycle. And here's why. I want to think about the graph of the tangent function. This is a little bit trickier to visualize with a unit circle, so we're just going to think about the graph. And notice that I've made a ty graph instead of an xy graph, since we're working with a variable of t. So here's minus pi over 2, and here is positive pi over 2. Here's my vertical asymptotes. Here is my tangent function. It looks something like this. So this is y equals tangent t. Now, notice that no matter what value I pick for c, no matter where I move this line, up or down, it will cross the tangent exactly once over this cycle. That means you always get one solution per cycle. That's actually really good news. It means we don't need to worry about things like doing plus or minus or doing pi minus the inverse. All of that subtlety goes out the window when you are talking about the tangent function. What does remain is that we can always shift the solution by a period. So this means, I'm going to have to erase this graph, I'm sorry. This means that we get one basic solution of t equals inverse tangent of c, but I can also get other solutions by shifting this by a multiple of the period. Now, question for you guys to think about for a minute. What is the period of the tangent function? Because it's not 2 pi anymore. It's actually pi. So I can take this and I can add any multiple of pi to it, and that gives me another solution. Otherwise, these problems work exactly like they did when we were dealing with sine or cosine. But we have to remember, it's not simply that, oh, you shift everything by 2 pi k. No, you're shifting it by multiples of the period. That's the key point. So you got to remember, what is the period of the thing that I'm dealing with? Let's take a look at an example of using this kind of thing in an application. So let's suppose that I want to solve tangent of 3x plus 1 is equal to 6. Now, it doesn't matter what this number is over here. You always get a solution. There's no worries about, is this in the correct range or anything. You're going to get a solution. And the solution is going to come from saying 3x plus 1 is the inverse tangent of 6, but it could also be shifted by a multiple of pi. And now I just have to solve for x. So I'm going to say this means that x is equal to inverse tangent of 6 plus pi times k minus 1, all divided by 3. And there's my solution. So in a lot of ways, these go similarly to what we did with sine and cosine, but in some sense, these are even easier because We don't even need to worry about doing a plus or minus out here. We don't need to worry about doing another option that's pi minus inverse tangent. There's none of that going on here. So I actually sort of started you out with the hardest case, which is sine, and now we have worked our way up to the easier cases, or the easiest cases, at least to me, these are the easiest, which is tangent, and as we will see in a moment, cotangent. So hopefully you guys have seen those other problems with sines and cosines enough here. Same kinds of deals can happen with tangent. I will let you guys practice those yourselves and see those. And make sure that you do take a look at the examples that My Math Lab gives you. They give you lots of great examples, and I'm really expecting you guys, especially now that we're not able to meet in person in classrooms, to really take time on your own and look at those and let me know if you have any questions about them that you want me to answer, because I'm always happy to answer those, but I do want to make sure you guys are actually looking at them. So our last thing is, what about if we want to deal with something like cotangent of t is equal to c? Well, same kind of deal is going to happen as with tangent. The solutions are going to be that t is equal to cotangent inverse c plus pi times k, and there will always be one solution per cycle. And the reason for this, it's not too difficult to see that this is true, because this is going to be the same kind of deal as what we had when we talked about tangent, except that this time, one cycle goes from 0 up to pi. We get vertical asymptotes here, pi over 2, and we get, I'm going to do a terrible job drawing this, we get something that looks like this. This is my y equals tangent of t. Well, if I have some y equals c line here, it will always intersect this tangent curve. Why did I say tangent? Cotangent. This is the problem with not having you guys in person to yell at me whenever I write something asinine like that. When I have y equals c, it will always cross this cotangent curve exactly once over this cycle, because this thing just runs from positive infinity down to negative infinity. Never turns around, never does anything like that. So any horizontal line has to hit it, and it has to hit it once. Can't hit it twice. But I can always shift things over by the period. So we're going to get this same kind of thing going on here. Okay, so let's see if we can use that to do a problem involving cotangent.